Hello and welcome to the next video lesson on atomic models with specification reference 3.1.1.1. And we have one learning outcome that we want to appreciate by the end of this video lesson, and we want to know and understand atomic structure and how it's evolved over time from the early days right through the present time. Okay, what we can do now is to review the last half dozen models of the atom, going back a couple of hundred years, and going back into the 19th century, the early 19th century. The model that prevailed was developed by John Dalton, and that was superseded by the plum pudding model by J.J. Thomson, which was then, after several interesting experiments, superseded by Rutherford's model. Now we're getting into the early part of the 20th century, which was then improved again by Niels Bohr, which prevailed for quite a while until the Bohr model was improved and modified, which is in fact the model of the atom that we work with at A level mostly. But it's not the most up-to-date model of the atom. The most up-to-date model of the atom is the quantum mechanics model. But that explains some things that the modified Bohr model can't explain. But it's quite tricky to get your head around at A level, and so most of the concepts that we deal with at A level can be explained by the modified Bohr model, and so that's what we spend most of the time on. So let's review each of these one by one. If we start off with Dalton's model, as I said, the early part of the 19th century, and what he said was that the atoms were like solid spheres. All right, so at least we got down to the fact that we've got an indivisible particle that was still from Greek times called the atom, and here we illustrate atoms of one type, one element, as being purple, and the atoms of another element being green. The colors just signify that the spheres are different from element to element. That's as far as that model goes. But then what happened was, in the latter part of the 19th century, electrons were discovered, and so these solid spheres couldn't be correct. So the experimental evidence falsified Dalton's model, and so Thomson came up with another model that explained and included the evidence for electrons, and that was called the plum pudding model, whereby small negatively charged particles were contained within a larger sphere that was the atom. So in the early 20th century, Rutherford and a couple of his students did the famous gold foil experiment, where they fired alpha particles at a very thin sheet of gold foil, and the results they got, which are explained in more detail in the next slide, basically falsified Thomson's model. And what Rutherford then developed was a model that included a very dense but small nucleus in the middle of the atom, surrounded by a cloud of the electrons that had been discovered. And he did that because some of these alpha particles, a small number of alpha particles, bounced back off the gold foil, and that couldn't happen if with the plum pudding model. And so we needed a much more dense, dense as far as mass is concerned, and also dense as far as charge is concerned. We needed a much more dense nucleus, and so that's why Rutherford modified the plum pudding model to the one that you see there, with a small positive nucleus surrounded by electrons. And then came Niels Bohr, who improved this still further, because what he noticed was that that electrons tended to have discrete amounts of energy, right? So they couldn't exist anywhere in this sphere that was the atom. They emitted or absorbed electromagnetic radiation of only particular frequencies, and those frequencies related to the difference between the energy levels in an atom. And so he put the electrons into energy levels or shells, and that was his breakthrough. Yeah, so in the Bohr model, then in a particular energy level or shell, it was said that each electron had exactly the same energy, and if it jumped between energy levels, it would either emit if it was going towards the nucleus, or it would emit electrons, yes, if it was going towards the nucleus, or it would absorb energy from outside, which would make it jump from one energy level to a further outer energy level. So that was the Bohr model, but what was found out by further experiments was that actually in an energy level, not all of the electrons had exactly the same energy level. So let me just draw this. So let's say we take this energy level here, right, and expand it. Okay, what we find is that the energy level, so that's the main energy level, it actually consists of sub-levels that we now call orbitals. So they found from experiment evidence that the electrons in a shell didn't all have exactly the same amount of energy. They had slightly different amounts of energy, and that went on to lead to the idea of there being orbitals within an energy level, and that became the modified Bohr, and that's the one that we work with at A level. But still further, we have the quantum mechanics model, which at A level all you need to really understand is that it's basically based on probability. So you can't say exactly where an electron is going to be, and you can have no certainty about that. All you can say is that there are parts of the atom where the electron is more likely to be. So you see in this picture there that you've got the dense part in the middle, and the density of all the dots is to signify the probability that the electron would be there. So what that dense bit in the middle there would represent the inner shell of electrons, and then you see here, I'll just draw it on here, you've got a space here, right, where there is a much lower probability because the dots are less dense in that part there, and that signifies the distance between energy levels. And so then you have another area, let's mark it in green, you have another area here where you've got a further dense area of probability where the electrons in the next shell are likely to be. And then as you get further out, you can see it maybe around here, you've got a much less dense area. So that's the edge of the second shell, and that would be part of the distance between the second shell and the third shell. Okay, so that's about all you need to know for about quantum mechanics at A level. And there we have the last half dozen models of the atom going back a couple of hundred years. But I think one of the reasons why this topic is in this spec is this, and that is that each of these models were falsified in time by experiments. All right, so scientists did experiments which the prevailing model couldn't explain, and so they had to update the model and improve the model that then could explain the latest experiments. And then time would go by and scientists would do different experiments, maybe more detailed experiments or experiments with better equipment, and they would then falsify that model, the current model, and the same process would carry on. And that is the scientific process, this process of falsification by experiment and then modification of models or theories or hypotheses. Okay. So these solid spheres are meant to represent the atoms in the Dalton or Thomson model. And what if this is the model of the atom that you believe, and you had a film of gold foil, which is the red atoms like that, and then you fired the alpha particles at them, then what you, or in fact Rutherford in his time, would expect is something like would happen here. See, these particles coming from the left are hitting the gold foil atoms and bouncing back, all right, because they were believed to be fairly solid. And this is the model before the plum pudding model. But what Rutherford did was he did this experiment, and he didn't notice this. The gold particles, the alpha particles rather, that he was shining onto the gold foil didn't bounce back like you see in this diagram. What happened was that you got something more like this, what will happen in a second. So here you can see the red dots, the small dots, are the nuclei of the gold atoms, and they are charged positive, as you can see, and circling around them are electrons in orbits of varying distance from the nuclei. And so what Rutherford did is he shone his alpha particles at the gold foil, and you see one coming from the left here, and what he actually found, to his surprise, was that pretty much all of them, most of them, would go straight through. But just like that one on the left there has hit the nucleus head on and bounced right back, and that was pretty surprising to Rutherford. Here's another one going to hit it, and it comes back. And he actually used the phrase, it's like firing a cannon at a sheet of tissue paper and having the cannonball bounce back at you. He was that surprised, but that's what he observed. Most of the particles going through, like you see here. I'll just increase the rate of the radiation, so you can see there's a few more particles coming at the gold foil now. And what he observed was that most of them went through, and occasionally one came back, like that one just there is coming back from right to left now. And so he used this observation to update the model of the atom. So hopefully that little animation there was clear for you to illustrate the famous gold foil experiment. And so, as usual, what we'll do is we'll just review our learning outcome for the lesson, and we were to appreciate that knowledge and understanding of atomic structure has evolved over time, and we also discussed how experiments falsify existing models and force scientists to improve those models. Okay, hopefully you've enjoyed that little video lesson, and I'll see you in the next one.